This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, so welcome everybody. So we're week 11 and we're almost at the end of it. And today I will take you through two presentations in one. They're somehow connected, but they somehow summarize as well in different ways some of the achievements of technological achievements we discovered before, from the beginning of the Industrial Revolution and through modernity. So the first part of this discussion will focus on skyscrapers, and I define them as ultimate skyscrapers, skyscrapers that in a way have pushed the boundaries of the technologies that we're employing in a particular period of time. And in the second part, I'll come back on glass, the modern glass. So the ultimate skyscraper, by all means, is certainly the Empire State Building. Now, the Empire State Building, as you probably know already, is the fastest skyscraper that was ever built, still to this date. So the efforts in the construction management of the structure was unprecedented, and to this day, still the fastness, the speedy outcomes of the erection of the structure of the Empire State Building is still being unmatched. What were the technologies involved? Well, in effect, they were the culmination of those technologies that were introduced in the late 1800s in Chicago, which we've seen in a previous lecture. It's the steel skeleton system that, as we saw in Chicago, evolved step by step. It was not necessarily introduced all at once in the home insurance building, as we discovered, but it was a process of constant evolution until we reached some landmarks like the Fisher Building or the Reliance Building that had this freestanding structure. There was clearly a skeleton, which means an array and a configuration of columns and beams all stacked together in a multi-story configuration. So the Chicago School of Architecture was not an isolated phenomenon. We saw there were also crossovers that reached Australia, but certainly New York was the other center of innovation. And so the technologies that somehow began in Chicago also evolved almost at the same time, if not simultaneously also in New York. So by the time we reached the 1930s, those technologies have been mastered, and skyscrapers start to take the shape and that characteristic that still describes them as speculative endeavors that tend to regenerate themselves. So this is a picture of the Waldorf Astoria building, which was the building that used to sit on the Empire State Building site, and that was demolished. It was a significant building for New York for a period of time. It was relatively tall, and it was demolished. And in the process of demolition, you can see there it's inside it. It's a skeleton structure along the lines that we described before. So what the Empire State Building did, what many other tall buildings have done before in the city, and they continue to do that. You raise down a previous building to put another one on top, which is bigger. The Empire State Building was a particular kind of development. It was not necessarily in the most dense parts of the city. It still stands as a standalone landmark in a way, which is part of its fascination and appreciation as a landmark still today in New York. But ultimately, it was a structure built to be bigger and to be also be built faster. It was built at the beginning of the Great Depression, so there was plenty of labor available, and it was built on a skeleton frame. You can see here the foundation works being set up. You can see somebody basically taking some measurements, and you can see a series of pits here, which are concrete pits that were set up and that dig underground and reach the famous bedrock of New York that allows many skyscrapers to stand directly on the rock below. And you can see there are some steel beams and grillages that were used there to host then steel columns. But what's really striking about the Empire State Building is not so much the technology, because as I said, it's the same one of the good old Chicago buildings in a way, just take it to another level. It was the construction management approach. What the builders did here, they set up an entire process of supply and distribution of material that was an industrial kind of production that took place on site. So you can see here a plan of the basement where there's a number of columns. You can recognize the grid here, and you can see also how many of them there are. This is the basement plan. So it's at the foot of the building. The tower will be only occupying one part of this. And this is a construction management plan that has a number of supply points where trucks with bricks or concrete trucks will come in and deliver the materials. Then these materials will be distributed using rail tracks installed temporarily on site, and then shifted to hoists and then taken over to the upper floors. Of course, in parallel with this, there were cranes or derricks to complete the material handling. And these are some pictures that illustrate this process. By the way, the entire process of construction of the Empire State Building is it's summarized in a book, which is quite hard to find, actually. There's only one copy in the ABP library. It's out of print, but years ago, Carol Willis and another historian, Friedman from New York, who's an expert of engineering and architecture of this period, wrote a brilliant book that is highly illustrated, that shows all the pictures of the construction of the Empire State Building, which was recorded by the builders. And this part of the documentation is in the Skyscraper Museum in New York. So the pictures I'm showing you here are from that publication. And you can see here how the materials, in this case, concrete, for example, was thrown into, loaded into these hoppers that then, or bricks, were discharged directly into this hopper. Then these hoppers will be taken to hoists, and then the hoists will deliver the materials vertically on site. So once this material will come out of the hoists, there was a number of elevators that were dedicated for the supply of material. Some of them were dedicated for the movement of personnel and workers. And then these materials were distributed along the perimeter of the building, which you can see here. This is the actual footprint of the tower. And you can see there's a rail track there that is being used to distribute all the materials on the typical floor. Now, obviously, once the floor is completed, then the rail track will be dismantled and craned to the upper floor, and the process continues. And these are some pictures of this track with some turntables, and you can see how workers were able to move and handle very large quantities of materials by not using cranes. And this is one of the reasons why the building was so successful. It was able to build itself from inside out. Cranes were still there, but they were used only for the erection of the steel frame. The steel frame of I-beams and custom-made profiles put together by rivets that you can see here sitting on the foundation. And you can see them here being craned up from the street level. The floors were then completed with concrete, and you can see here a process where the concrete slab is being stripped by its formwork. And the facades were also built using this method of supply, using hoists and the rail track inside the building, using limestone spandrels and aluminum frames. In this case, you can see how one panel has been installed there using a Lewis, one of those devices that we discovered in the first module, and the second one when we spoke about historical methods of construction. So the methods, of course, in this case are different in that they rely on this mechanical system of conveying materials through the floors, but some of the good old principles of construction still carry on timelessly. And this is a picture when the building was completed. Look at the date there, 19 September 1930. The first picture I showed you before when they were setting out the foundation was January 1930. So in 9 months, the entire skyscraper was, the structure at least, was topped out, which means it reached its tallest part. The construction continued later on. There was also master was to be installed, of course, the fittings and the finishes, but that still stands today as a record. So why did that happen? Well, it happened because of this very clever management system, but it also happened because at that particular point in time, there was plenty of availability of labor in New York. And so it was in a particular period of time as well, where yes, it was very fast, but also the amount of labor involved was available, and it was being able to be implemented on an industrial scale for a construction site. Now, this as a brief intro to take you to the next topic, which is how another stage of the evolution of skyscraper took place after World War II. Much, as you know, a lot of the skyscrapers that we appreciate in architectural history were built after the Second War conflict in the last century, and they were built in the United States. I will not cover all of them, but I would like to focus back on Chicago and indicate how, thanks also to the work of one engineer who's depicted here, Fazlul Khan, there are some significant buildings that were built in Chicago that sort of have an interesting continuity in a sense with the birth of the skyscraper, but also have an interesting precedent because they somehow set the scene and they reached the limits of the technological developments of that time that created the conditions for the high-rise construction that we have today. So who was Fazlul Khan? Fazlul Khan was an engineer, structural engineer of Bangladesh origins, who used to work for Skidmore, Owens Merrill, SOM. Now, SOM are very well known as architects. They're the same architects of the Leather House, many other important buildings, but SOM had different, and still has, different offices in different cities that operated almost on a competitive with a competitive spirit. So the New York office of SOM traditionally, which was led by Gordon Bunshaw, for example, was not necessarily working all the time with the Chicago office, which was instead led by the architect Bruce Graham. And Fazlul Khan sort of rose under Bruce Graham's sort of period of architecture. And he managed to establish with Graham a very close collaboration where structural engineering was the essential expression also of the building. So there's a number of buildings that are both architecture and structural engineering, and they're very significant because they combine the two things. It's very hard to say to what extent the engineer was driving the outcome as much as the architect. And so Khan is often considered one of the most important engineers of the 20th century because given this particular relationship that he established with Graham within SOM, he was able to experiment different structural topologies that also led to some important buildings, one of which is also here in Melbourne, by the way, and we'll come to that. Now, some of you who have taken the subject with me in architecture technology may have seen some of these slides before. But what I wish to do here is just to give you the historical context in which these developments happened. And you would be familiar, some of you will be already familiar with the concept of the premium for height. So Khan was the engineer who defined this and divulged this idea that in order to build efficient tall buildings, you have to consider the impact of wind as the primary governing factor for the structural design. And so he was well aware of this problem throughout his career. And in the early 1970s, he wrote an article in an engineering journal, the Steel Journal, that was published also first in UK, in America, and also here in Australia, where he basically presented the problem with this chart and this analogy. He said, well, if you imagine you have two buildings that are exactly the same, and you put one inside a glass, an hypothetical glass dome, so that you remove all the effects of the wind, and you compare that with a real building, which is actually exposed to the environment, then you will find that the building that is under a glass dome that has no wind effect has a structure that works with very simple principles. The taller it is, the more steel you need in a proportional way. And so here is this line that goes here from this point to that point. It simply says, if you double the amount of floors in your building and there's no wind, you have to double the amount of structure involved, steel in particular. Steel is usually priced by the weight. But in reality, when you're looking at a tall building, if you double the amount of structure under the wind, you might not have to simply double the amount of steelwork, but you have to have put 3 to 4 times more the amount of steelwork because of the effect of the wind. So in other words, the taller you go, and the more the impact of wind is felt, to the point that you can have a situation where above a certain limit, the amount of steel that is required to withstand the wind is much more than the one you need to simply resist the weight itself of the building. So there is a premium that increases with height, in tall buildings, that is in terms of costs of the structure. So why this is important? Because this is the beginning of concepts of efficiency. Now, this is not the buildings I'm showing to you now. They're not necessarily efficient anymore by current standards. Certainly not efficient from an environmental perspective like we would today. But the framework of thinking about this is important, because these buildings show how the necessities imposed of a very large structure impose you to be restrained and to be very careful about the materials that you use. Okay, so there's a contemporary appeal about this evolution of buildings, because it shows you how, by combining engineering and architecture, Kant was able to get the ultimate responses for those projects. Yes, they were tall. You might argue, I could, if you want to be really strategic, could have said, were they necessary in a socioeconomic context? Probably not. They were sometimes speculative. But the built outcomes were efficient. They were the most economic outcomes you could possibly have at a particular point in time, that make no frills about the architecture, because it just tried to reduce the problem to the minimum elements. So Kant started to experiment with Graham along these grounds in Chicago. And one of the first buildings he built was this one, which is the Chestnut Dewitt Apartments. This building is important because it's the first tubular structure where Kant realized, if I have a tall building, and the tall building is, by and large, a cantilever structure that is fixed to the ground, what if instead of having a forest of columns inside, like the Empire State Building, I just put all the efforts and all the structure along the perimeter of the building? And I'll just rely on that network of columns and beams in the perimeter to withstand the wind structure. Of course, there's a core in the middle, but it's basically separating here the function between the resistance of the wind from the resistance of the loads inside the structure. And so this is not a very tall building. It's in Chicago. It's not far from the famous Lakeshore Drive building of Mies van der Rohe. You could see them here on the right. But it's testing this idea, the tubular structure. All I need is an external skeleton, and the rest inside can be lighter, and it can be also cheaper in a certain sense. Now, this concept was also picked up by other engineers at SOM in San Francisco, who started to adopt this idea. What if we put all the efforts at the perimeter of the building? And it doesn't have to be a grillage of columns and beams, but it can also be a reticulated structure, like a digrade in this case. And we can do that with steel, like in the precedent example. We can also do it in concrete, like in this case. So you can have a grid of panels here that are solid, that you can clearly see are acting like a bracing frame, and they're just running around the perimeter of the building. Yes, there is things inside, like lifts and mechanical ducts, but they are simply there to allow for the floors to be supported. So they're not picking up all that additional effort that's required by the wind. And Kant, again, with Graham, put also to the test this idea in this other apartment building, where you have, again, the brace frame that becomes part of the expression of the building, that it's revealed on the outside. This is a wonderful apartment complex, again, in the same area that Dewitt Chestnut place in Chicago. And you can see here again how the idea is applicable for concrete as much as it was with steel. So it's the idea of having a digrade and a perimeter framework that is able to withstand the wind. But there's another important project that Kant did, and And he was able to experiment it when he had this opportunity to collaborate with Duncan Freeman here in Melbourne. There's a long history behind BHP House, which could probably be worth a lecture standalone. But just let me mention that there was a job that was given to a local architect, Duncan Freeman, at that time, who never did anything of this size before. And Duncan Freeman were relatively concerned about the structural implications of a job like this. They wanted to have some advice. There was some precedent relationship between Melbourne architects and American architects that took place. There's other buildings around BHP House today that you can see, like AMP Square, which saw the contribution from American architects, particularly from the San Francisco office. But Barry Patton, the leader of Duncan Freeman at that time, he decided to resort not to the San Francisco office of SOM, but to the Chicago office that had Fazlul Khan there, because the idea was to have a building that could express steel, being a building from BHP, as the key part of the expression of the building. So you probably know part of this already, but Duncan Freeman actually went to Chicago for a period of time. The key designers, they stayed in SOM's office. They collaborated with Khan there in Chicago. They conceived the building. They put on the table many options until Khan proposed one of these ideas that was just ringing in his head. And this idea was not necessarily the tubular structure, but was an evolution of that. The idea was like, if we now have a building that we can brace, not by using a continuous envelope all around, but by using a series of belts and riggers that you can see here in the picture. He was sort of playing with this idea in other buildings that did in the United States, and he saw an opportunity with Duncan Freeman to test it here in Melbourne. So once that became clear in the heads of the designers, then Duncan Freeman came back to Melbourne, and they adopted that idea. They developed it with a local engineer, Irwin and Johnson, and they were able to build the first structure in steel in the world that had the first belted out rigger system of resistance to the wind. So what it is, it's basically a building that has a core that in some levels is restrained and it's connected with the perimeter structure with a number of trusses that outrig, which means they cantilever from the core and they connect to the perimeter frame. So you can't see here in the picture, but there are some trusses here behind the facade that connect back to the core of the building. And these columns, you can see them here in the picture, they carry all the way down to the ground. And they are tapered, by the way, because as the loads from the top to the bottom become bigger, the stresses inside the columns also increase. Well, these columns are anchored to the ground and they're connected to the trusses and also here at the top and back to the core, and they help to stabilize the building. So rather than putting all the efforts around the perimeter, in this time, we are concentrating all the muscles on the skeleton of the building only in some particular locations of the tower. So it's another step towards the efficiency that was implemented particularly here in BHP House. BHP House was not the first outrigger structure in the world. There was some precedents in concrete done before, but it was the first steel structure. And it puts it on the map, I suppose, as a building that it's important for the evolution of high-rise worldwide. Most of the mega tall buildings you see today still use this principle that was implemented here at BHP House for a larger scale. This is a building that was only 180 meters tall, not particularly tall, but the principles behind were very advanced. So what is the benefit of that? It's a benefit of efficiency of saving materials, because by introducing these belt trusses, you're able to reduce the sway at the top of the building, which means that you can save structure, you can save material. And you can see here a chart again that gives you a comparison by this is how much sway you may have had at this point, where obviously going to the right becomes bigger. If this is the amount of deflection you would have had at the top of the building without the trusses and the belts, this is in effect the amount of sway that was achieved with them. So you're reducing the amount of sway, means you have less material needed, less money, but also I suppose, less of everything, less labor, and less potential also waste. There's another step in this evolution, again, going back to Kahn, where Kahn started to play also with concrete. It wasn't just about steel during the 70s. And he took the concept of the initial idea of the tube a bit further by understanding that perhaps to put all the efforts at the corner of, at the perimeter of the building wasn't always the best solution. And there was another way to make use of the fact that some structures, because they already have a core inside, they offer an opportunity to build a service core in concrete and a perimeter structure together, and to consider them as two tubes, one inside the other. You have to build the core anyway, so you may as well make that structural. So again, this is the next evolution in the concept. It's sort of stemming from the idea of the Belts and outrigger, where you had that idea of using the core to stabilize the building using the perimeter and the belts and trusses. But here you have instead a continuous core and a continuous perimeter that are acting in concord, and they're helping each other to complete the building. You can see it used here in Houston, another project by SOM. And you can see it in place using concrete as a tube in tube. So there's some shear walls that are inside here and some perimeter frame that goes all around and restrains the building. There is something quite different here you probably have noticed. It's the fact that the columns increase in some areas of the building. So why would that be the case? If the idea was to have a continuous tubular frame all around, and being efficient and repetitive and economical, why would you have a situation where the columns increase a bit more? Is that an aesthetic choice? Well, it wasn't. Again, here was Graham and Fazil-Khan working together, and they bumped into a problem with tubular structures. Once the footprint starts to grow, the fact is that the stresses induced by the wind along the perimeter of the building, they're not always the same. They actually become bigger towards the corner of the building. And so in a tubular structure, you have to be careful, because even if it looks all the same all around the perimeter, the fact is that some areas of the tube are more stressed than others. And so what they're doing here, well, when I have less stresses, I can have a normal typical column like this. But when I get to the points where the stresses increase, we're going to put a bit more material in there to overcome that problem. And this is the problem that you can see it pronounced here in this sort of bulging of the tube on the external structure, right? That's a problem also that led to the development of the Sears Tower that we'll use to conclude this presentation today. So all in all, what happens here is that you have an engineer working in an architectural firm who's able to experiment these very innovative concepts, where the ultimate goal here is to save material. And saving material is important, and it's still a very contemporary problem. You don't want to waste. You don't want to use more materials than you need in architecture. And the skyscrapers are one of those typologies that have forced engineers to think really hard about this, because otherwise projects wouldn't go ahead. Okay, so there's other aspects about this saving of material that implied also saving energy during the operation of the buildings, because the tall buildings are very expensive to build. They're also very expensive to maintain. So there is an inherent need to be efficient about it. They're not an efficient solution that resolve the problems of the built environment. But once they're built, they need to, in order to survive and last long, they need to be efficient for what they are. Okay. And so Kahn ultimately, in a space of 20 years, was able to implement several of these solutions that take us from the rigid frames of the Chicago School, the Reliance Building, and the Empire State Building, through other experiments like the belts and outrigger trusses that you can see here. This is BHP House. The tubular structures that we saw, like the apartments in Chicago, the David Chestnut, and other tubular structures that are very, very tall that I will now introduce and give you some examples. So this is the premium for height that takes place also with it's sort of overlapped here with appropriate typologies that become more relevant depending on the height of the building. Okay, so Akan was able to experiment all this through his career. He was in a very fortunate position, but it was certainly also a position that left a big, long legacy. There could be other engineers I could mention, like Leslie Robertson, but again, for reasons of brevity, I want to focus on Chicago. And so to conclude on this, I'd like to just take you through some important buildings that happened in Chicago as a result of Kahn's activity, but also as a result of the influence of Kahn's work that were picked up by others. And these are 3 examples that there could be many more, one of which is inevitable to mention, and I will, which is not in Chicago, but in New York. And so the first example is the John Hancock Center in Chicago, which is an interesting hybrid structure. It is a tubular structure, in effect, that has been braced. So the initial concept here was to have a larger tube only at the perimeter of the building, until, for the reasons that I was saying before, because of the sheer size of the structure, they realized that the stresses in some parts of the structure were too high to be withstood by a simple tube. And so if you observe the building closely, you find that there is a series of columns, yes, all around, but of course there are also these bracing frames that just come around the tower, and they come all the way down. The tower tapers because it's a mixed-use tower, probably the first mixed-use skyscraper, which means it has an office part at the bottom and some residential apartments at the top. And the structure was very cleverly conceived as a number of tiers that are conceptually similar, but they're of course change in size as you go up, because the footprint reduces itself as you go up. And you can see here this diagram from Kahn that indicates the amount of stresses on the structure at the corner of the building. And you can see how these diagrams here are saying, you know, the stresses here at this corner sort of grow, and they become much bigger towards the corners. And they are much bigger at the lower part of the building than they are at the top. Those are simply actual stresses under the wind. So that's just the amount of stress that is induced into the tower by the wind alone. Then there's the other component, which is the weight of the tower itself that counterbalances that. And so the idea is to have a very simple concept that is repeated as you go up, where you have a fairly conventional structural system at the perimeter that is braced by these primary ties. And within those, there is also a number of secondary ties that you can see indicated here with some thicker lines. So it is a building within a building that it's rigid enough to be connected to the next, like a block that it's tapering as you go up. And inside, you have no concerns whatsoever about the wind. All you have to worry about is to have a core, yes, to withstand, of course, the loads of the floors, to take care of lifts and ducts. But you can see that all the perimeter structure is doing the work. So everything that is needed to resist the wind is very much around the perimeter. You can see these very large columns. There is also some bracing diagonals that will come into place. But in between the core and the perimeter, it's just beams to support the floors. And here's the building under construction. This is a picture here on the right of one of these very large columns that you can see them carrying out here. And in this case here on the right is depicted when it hits the foundation at the bottom, and then the diagonal ties that keep them together. And you will, if you look closely here, you'll find some of the horizontal edge beams here every 3 floors. They are thicker than the other ones because they're also connecting with these diagonals and acting as ties to prevent the tower to burst from the effect of the wind and from the effect also of the dead loads of the structure itself. Again, a picture here, you can see now how the tiers are coming together and they continue to raise up. And you can see that what's coming first here is a grillage with the core that it's allowing to build the structure. So you can also install, you can handle materials and so on. And you can observe how the columns come first. This is probably one of those larger beam ties I was referring to before. And in parallel with that, you can see how the diagonal members also come in sections. So the sections were very large pieces of steel that were prefabricated in a factory. You can see them here on the right, whilst they were being built in a workshop. And then they were bolted and welded together on site. So using a combination of high strength bolts and welding, these connections became rigid. You can see these enormous gusset plates here. It's like building a giant truss. It's like building a bridge in the sky, some have said. And again, you can see here the picture. This is the 12th floor, arguably, and you can see the large columns, very large. They are tied by these diagonals throughout. And shop drawings that were developed by the engineers to conceive it. This would show you more in detail the fact that there's a combination of bolts. They're not rivets anymore. The rivets industry has been very much wiped away after World War II because of introduction of arc welding. But high strength bolts, on the other hand, continue to replace rivets. And ultimately, the structure was clad in aluminum, and the aluminum also covering the structure was insulated, because Chicago, being a city that has very extreme temperatures in winter and in summer, Chicago can be very, very hot in summer and extremely cold in winter, as you probably know. The structure in steel, in this case, can be subject to significant variations in temperature that can lead to problems of localized stresses induced by the temperature. So the whole structure then is clad with aluminum, not steel as you might think. So this is not very much of a steel tower after all. The steel is inside, but the aluminum is what gives it this very dark metallic appearance. Now, the other tubular structure we could talk about is the World Trade Center that there is no more, that used to be. The Twin Towers in New York. And I thought I should just mention it here to highlight that this is by all means not just about Chicago. But rather than focusing on the Twin Towers, I'd like to speak about another building that it's less known. It still stands though, and again, it's in Chicago. That very much has the same concept of the Twin Towers, and it is a pure tube. What it means is that, again, all the structure, all the masses of the structure are on the perimeter of the building. The core is supporting just services and helping to support the floors. And the structure was also very interesting because it's using the perimeter of the building also to run services. So you can see here you have a close-up detail that was designed by, prepared by the architects in this case, Perkins and Will and Durrell Stone, in collaboration with an engineer, Alfred Picardi, who was very close with Kahn. In fact, he actually collaborated with Kahn in the John Hancock Center. So some of those ideas that Kahn had at SOM were then transferred to others, and the whole generation of engineers in America in the 70s started to implement them in other structures. So here what you're seeing is a building that has all the structure at the perimeter, and that perimeter is also functioning as a way to reticulate services, water, air conditioning, supply and return here. And all you have in between the core and the perimeter, therefore, is just free space. The building is clad eventually with stone, and you can see the stone coming up here on the lower floors. But what's inside is a lot of steel, plenty of it, and a steel that is used as a combination of V masts and columns and edge beams. And these were basically prefabricated sections that were like, they were known as tree structures, where you can see a V profile there of steel. That is about 2 floors or a few more, probably 3 floors higher, I believe. And you can see one piece there that it's coming pre-welded with pre-welded connections here that are half of the edge beam of the structure. So you can see there is an element that it's repeated all the time, which is the same approach that was used also in the Twin Towers. And these elements are connected on site to create this continuous envelope that it's not just facade, it's also structure in the building. You can see how these three elements are craned up. There's 3 floors involved here, 3 floors at a time. So it's efficient to build. You just put these things up. That's the primary structure. Once you have that in place, you're able to fix the floors back to the core, and you're done with the structure. And you've done 3 floors at a time. Okay, so there's an element of speed here involved. And you can see the back of these masts that are also have a horizontal member that runs through. And that's used to fix some trusses that you can see here at the back in this drawing. So you can see here on the left, just a simple configuration of the steel involved. And then at the back of it, you have the continuous plate that is used to fix trusses that take back to the core. And the trusses are then used, of course, to support the floors. In this case, you can see them here being sprayed with vermiculite to make them fireproof. So that's a pure tube where you have just structure on the perimeter of the building to withstand the wind. But there's another and one last example I want to mention, which is very much the child of Khan. And this is the ultimate tube, because there's not just one tube, but a number of tubes all put together. And this is the Sears Tower. Now, the Sears Tower was the largest building ever conceived at that time. It stood up as the tallest structure in the world for many years. And the idea was to have a very large footprint, even larger than the World Trade Center in New York. Too large, and so large that to use a tubular structure like the one of standard oil building we just described was not efficient anymore. Why? Well, it was not efficient because of that problem that we encountered in the building in Houston. And the problem is the so-called shear lag, where when you have a tube that it becomes too big, the difference in stresses from the middle part of the tube to the corners becomes so pronounced that you have to have 2 different kind of structures involved. So the brilliancy here of the engineer was to understand that, well, if I can't do that, how about I break down this very large tube, which was 75 feet, which is quite large. What if I break it down instead in a number of smaller tubes and I connect them all together? So this is the famous bundle tube configuration, where you have, instead of having a large unique tube, you connect all these tubes together. And there's a price to pay, which is the fact that some of the perimeter structure that normally wraps around the tube is going to also cut through the floor plate in these points, for example. Right, so you can see here how the tubes are returning inside the perimeter of the building. Now, that's not a big price to pay if you have a very large floor plate, because there's so much space anyway that you can afford to have every single cell here to have sufficient open space. But this is the idea that then allows you to have some of these tubes to continue taller than the others, and some of them to stop shorter, because arguably otherwise the areas produced would have been too much. In fact, this building was by all means too much, in the fact that for many years also had a lot of space that remained vacant. And you can see here in the diagram here where Khan is explaining the consequence of the shear lag problem that induced some of the structure to be not as efficient as it would be by instead breaking it down in smaller sections. And then, of course, the idea becomes also the architecture, where some of the tubes stop shorter than the others, and they create this pyramidal pinwheel that is characteristic of the Sears Tower. But how was that built? Well, the technique for building was similar to the one of the standard oil building. It was in line with the World Trade Center as well. And it's this generation of buildings where you create a singular element of columns and beams. You make it as big as you possibly can, and you stack it, and you continuously install it, starting from the perimeter of the building and then working yourself from the outside in. So here you can see the tower being under construction. You can see its footprint, and you can see how here, part of one of these cells of tubes is coming up, and you can see how some of these tube wraps around. You can see the foundations of one of them coming also inside. So the structure is not only on the outside here, but it's also returning inside, and it's connecting all these bundles together. These tubes were then connected horizontally by a number of belts that sort of connected not only vertically, but also horizontally. And you can see here how the delivery of these very large elements, trucks that sort of bring over very large columns with pre-welded connections for the beams. And here you can see the typical element that it's repeated many times. You can have, in this case, unlike the standard oil building, you have a column that is spanning 2 floors that is already coming with half of the edge beam for 2 floors involved. You can see that there, repeating on the other side symmetrically. And then what's happening on site is that you complete, and by the way, these columns also have perforations to allow for services to come through on the perimeter of the building, air conditioning in particular. And so once one of these trees is in place, it's then connected using some splice plates and some welding, and then the floors can come on top to complete the structure. Okay, so a very simple concept repeated throughout, but very ingenious approach that tries to make the best use of the material available. Again, prefabricated by and large and craned up in sections ready to go, ready to be bolted and welded on site. And you can see the scale of these impressive structures, and as well as the craziness of the health and safety regulations in the 70s. You can see obviously some of the standards that were acceptable in those days are not anymore. So I'll finish here on this part because I just want to carry on to the next one. But if there's any questions or any comments, I'll be happy to hear from you.